Diseases of ear, nose and throat and head and neck surgery by P.L. Dhingra. Chapter 2, Peripheral Receptors and Physiology of Auditory and Vestibular Systems. Auditory system. Organ of Corti. Organ of Corti is the sense organ of hearing and is situated on the basilar membrane. Important components of the organ of Corti are tunnel of Corti, hair cells, supporting cells, tectorial membrane. 1. Tunnel of Corti. It is formed by the inner and outer rods. It contains a fluid called cortilymph. The exact function of rods and cortilymph is not known. 2. Hair cells. They are important receptors of hearing and transduce sound energy into electrical energy. Inner hair cells form a single row while the outer hair cells are arranged in 3 or 4 rows. Inner hair cells are richly supplied by efferent cochlear fibers and are probably more important in the transmission of auditory impulses. Outer hair cells mainly receive efferent innervation from the olivary complex and are concerned with modulating the function of inner hair cells. Differences between the inner hair cells and outer hair cells are given in table 2.1. Supporting cells. Data cells are situated between the outer hair cells and provide support to the latter. Cells of Henson lie outside the data cells. Tectorial membrane. It consists of gelatinous material with delicate fibers. It overlies the organ of Corti. The shearing force between the hair cells and tectorial membrane produces the stimulus to the hair cells. Nerve supply of hair cells. 95% of afferent fibers of spiral ganglion supply the inner hair cells, while only 5% supply the outer hair cells. Efferent fibers to the hair cells come from the olivocochlear bundle. Their cell bodies are situated in superior olivary complex. Each cochlea sends innervation to both sides of the brain. So we can see the diagram 2.1, structure of organ of Corti. Here we have the stria vascularis, spiral ligament, cells of Claudius, spiral ligament, Dater's cells, Watcher's cells, basilar membrane, tunnel of Corti, fibers, nerve fibers, unmyelinated, cochlear nerve fibers which are myelinated, spiral ganglion, inner hair cells, tectorial membrane, outer hair cells, cells of Henson, and Reissner's membrane. Differences between inner and outer hair cells. Inner hair cells, total number, inner hair cells 3500, outer hair cells 12,000. Rows, inner hair cells 1 row, outer hair cells 3 to 4 rows. Shape, inner hair cells flask shape, outer hair cells cylindrical. Nerve supply, inner hair cells primary afferent fibers and a very few efferent. Outer hair cells mainly efferent fibers and very few efferent fibers. Development, develop early, develop late. Function, transmit auditory stimuli. Modulate function of inner hair cells. Vulnerability, more resistant, easily damaged by ototoxic drugs and high intensity note. So this is the auditory pathway from the right cochlea. Note the bilateral route through brainstem and bilateral cortical representation. So here we have the auditory radiations. We have auditory cortex, area 41. Then we have a medial geniculate ganglion or medial geniculate body. We have inferior colliculus. We have the innervation. Then we have nucleus of lateral lemniscus. Then we have lateral lemniscus, superior olivary complex, trapezoid body, cochlea, eighth nerve, ventral and dorsal cochlear nuclei, and auditory radiations. Auditory neural pathways and their nuclei. Hair cells are innervated by dendrites of bipolar cells of the spiral ganglion, which is situated in Rosenthal's canal running along the osseous spiral lamina. Axons of these bipolar cells form the cochlear division of cranial nerve 8 and end in the cochlear nuclei, the dorsal and ventral on each side of the medulla. Further course of auditory pathways is complex. Form from cochlear nuclei, the following are main nuclei in the ascending auditory pathways, sequentially from below upwards: superior olivary complex, nucleus of lateral lemniscus, inferior colliculus, medial geniculate body, and auditory cortex. The auditory fibers travel via the ipsilateral and contralateral roads and have multiple decussation points. Thus, each ear is represented in both cerebral hemispheres. The area of cortex concerned with hearing is situated in the superior temporal gyrus, that is, Brodmann's area 41. For auditory pathways, remember the mnemonic E. coli ma. Eighth nerve, cochlear nuclei, olivary complex, lateral lemniscus, inferior colliculus, medial geniculate body, and auditory cortex. Physiology of hearing. Any vibrating object causes waves of compression and rarefaction and is capable of producing sound. In the air at 20 degrees Celsius and at sea level, sound travels at a speed of 344 meter per second. That is 120 feet per second. It travels faster in liquids and solids than in the air. Also, when sound energy has to pass from air to liquid medium, most of it is reflected because of the impedance offered by the liquid. Mechanism of hearing. A sound signal in the environment is collected by the pinna, passes through external auditory canal and strikes the tympanic membrane. Vibrations of the tympanic membrane are transmitted to stapes foot plate through a chain of ossicles coupled to the tympanic membrane. Movements of stapes foot plate causes pressure changes in the labyrinthine fluids which move the basilar membrane. This stimulates the hair cells of the organ of Corti. It is these hair cells which act as transducers and convert the mechanical energy into electrical impulses, which travel along the auditory nerve. Thus, the mechanism of hearing can be broadly divided into mechanical conduction of sound, that is, conductive apparatus, transduction of mechanical energy to electrical impulses, sensory system of cochlea, conduction of electrical impulses to the brain, that is, neural pathways. Conduction of sound. A person underwater cannot hear any sound made in the air because 99% of the sound energy is reflected away from the surface of the water because of the impedance of the offered by it. A similar situation exists in the ear when air conducted sound has to travel to cochlear fluids. Nature has compensated for this loss of sound energy by interposing the middle ear, which converts sound of greater amplitude but lesser force to that of lesser amplitude but greater force. This function of the middle ear is called impedance matching mechanism or the transformer action. It is accomplished by A. Lever action of the ossicles, B. Hydraulic action of tympanic membrane, C. Curved membrane surface. Lever action of ossicles. Handle of malleus is 1.3 times longer than the long process of incus, providing a mechanical advantage of 1.3. Hydraulic action of tympanic membrane. The area of tympanic membrane is much larger than the area of the stapes foot plate. The average ratio between the two is 21 is to 1. As the effective vibratory area of tympanic membrane is only two thirds, the effective areal ratio is reduced to 14 is to 1. And this is the mechanical advantage provided by the tympanic membrane. The product of a real ratio and lever action of ossicles is 18 is to 1. According to some workers, Weaver and Lawrence, out of a total of 90 millimeter square area of human tympanic membrane, only 55 millimeter square is functional and given the area of stapes foot plate, 3.2 millimeter square. The areal ratio is 17 is to 1 and total transformer ratio is 17 into 1.3 is 22.1. Curved membrane effect. Movements of tympanic membrane are more at the periphery than at the center where the malleus handle is attached. This too provides some leverage. Phase differential between oval and round windows. Sound waves striking the tympanic membrane do not reach the oval and round windows simultaneously. There is a preferential pathway to the oval window because of the ossicular chain. Thus, when oval window is receiving wave of compression, the round window is at the phase of rarefaction. If the sound waves were to strike both the windows simultaneously, they would cancel out each other's effect with no movement of the perilymph and no hearing. This acoustic separation of the windows is achieved by the presence of an intact tympanic membrane and a cushion of air in the middle ear around the round window. Phase differential between the windows contributes 4 decibel when the tympanic membrane is intact. Natural resonance of external and middle ear. Inherent anatomical and physiological properties of the external and middle ear allow certain frequencies of sound to pass more easily to the inner ear due to their natural resonance. Natural resonance of external ear canal is 3000 Hz and that of the middle ear is 800 Hz. Frequencies most efficiently transmitted by ossicular chain are between 500 to 2000 Hz, while that by tympanic membrane is 800 to 1600 Hz. Thus, greatest sensitivity of the sound transmission is between 500 and 3000 Hz, and these are the frequencies most important to man in day to day conversation. Transduction of mechanical energy to electrical impulses. Movements of the stapes foot plate transmitted to the cochlear fluid move the basilar membrane and set up shearing force between the tectorial membrane and the hair cells. The distortion of hair cells give rise to cochlear microphonics, which trigger the nerve impulse. A sound wave, depending on its frequency, reaches maximum amplitude on a particular place on the basilar membrane and stimulates that segment. Traveling wave theory of von Beckesi. Higher frequencies are represented in the basal turn of cochlea and progressively lower ones towards the apex. Neural pathways. Hair cells get innervation from the bipolar cells of spiral ganglion. Central axons of these cells connect to form the cochlear nerve, which goes to the ventral and dorsal cochlear nuclei. From there, both crossed and uncrossed fibers travel to the superior olivary nucleus, lateral lemniscus, inferior colliculus, medial geniculate body, and finally reach the auditory cortex, situated at the middle of superior temporal gyrus, that is Brodmann's area 41. Natural resonance and efficiency of auditory apparatus. External auditory canal 3000 Hz. Tympanic membrane 800 to 1600 Hz, middle ear 800 Hz, and ossicular chain 500 to 2000 Hz. Transformer action of middle ear. Hydraulic effect of tympanic membrane and lever action of ossicles combine to compensate the sound energy loss during its transmission from air to liquid medium. So we have the tympanic membrane, axis of movement of ossicular movement, and this is a stapes. Effective vibratory area of tympanic membrane 45 mm square, foot plate area 3.2 mm square, aerial ratio 14 is to 1, lever ratio, that is ossicles, 1 is 1.3 is to 1, total transformer ratio 14 into 1.3, that is 18.2 is to 1. Frequency localization in the cochlea. Higher frequencies are localized in the basal turn and then progressively decrease towards the apex. 20,000, base 8,000, 4,000, 2,000, 1,500, 1,000 for 600, and apex, towards the apex it goes as low as 100. Traveling waves create maximum displacement of basilar membrane according to frequency stimulus. Higher frequencies are towards the stapes and low ones towards the apex of cochlea. This is 8,000 Hz, this is the apex, and this is the base. We have 3,000 Hz. Electrical potentials of cochlea and cranial nerve 8. Four types of potentials have been recorded. Three form from the cochlea and one from the cranial nerve 8 fibers, which are as follows: endocochlear potential, cochlear microphonic from and a summating potential from the cochlea, and compound action potential from nerve fibers. Endocochlear potential. It is a direct current DC potential recorded from scalar media. It is plus 80 millivolt and is generated from the stria vascularis by sodium potassium ATPase pump and provides source of energy for cochlear transduction. It is present at rest and does not require sound stimulus. This potential provides a sort of battery to drive the current through hair cells when they move in response to a sound stimulus. Cochlear microphonic. When basilar membrane moves in response to sound stimulus, electrical resistance at the tip of the hair cells changes and allow flow of potassium through hair cells to produce voltage fluctuations called cochlear microphonics. It is an alternating current AC potential. Summating potential. It is a DC potential and follows envelope of stimulating sound. It is produced by hair cells. It may be negative or positive. Summating potential has been used in diagnosis of Meniere's disease. It is superimposed on cranial nerve 8 action potential. Both cochlear microphonic and summating potential are receptor potentials as seen in other sensory end organs. They differ from action potentials in that they 1. Are graded rather than all or none phenomenon, 2. Have no latency, 3. Are not propagated, 4. Have no post response refractory period. 4. Compound action potential. It is an all or none response of auditory nerve fibers. Theories of hearing. In the past, two theories of hearing were popular: resonance theory or theory of Helmholtz, also called the theory of peripheral analysis. Two, theory telephone theory or theory of Rutherford, also called the theory of central analysis. But now the theory of von Beckesi is widely accepted. It propounds the frequency analysis takes place peripherally at the cochlea and continues right up to the cortex. According to the resonance theory, if a tone is struck, the structures attuned to that frequency also vibrate. The basilar membrane stretching between osseous spiral lamina and lateral wall of cochlea has the smallest width near the basal turn of cochlea and progressively increases towards the apical turn. The fibers of the basilar turn are also minimally tense and thus resonate in response to higher frequencies. As the length of fibers increase towards the apex of cortex cochlea, lower frequencies start resonating. In other words, analysis of speech frequencies occurs peripherally at the level of cochlea. In the telephone or Rutherford's theory, the cochlea simply collects the sound, converts it to electrical signals that are transmitted through the auditory nerve to the brain, where the sound is analyzed. That is theory of central analysis. It is likened to the model of a telephone, where telephone receives sound or speech and converts it into electrical impulses which passes through wires, auditory nerve fibers, to be reconverted to sound at the level of the brain of the listener. Cochlea, like a telephone, does not analyze the sound. Traveling wave theory of von Beckesi is presently the most accepted theory. Von Beckesi, while working on experimental models, shared that sound waves travel along the basilar membrane. These sinusoidal waves peak at specific places according to the frequency of sound, the higher ones near the base of cochlea and the lower ones near the apex. Thus, it shows tonotopic localization at the level of the cochlea, and such tonotopic localizations have also been demonstrated at the level of inferior colliculus, medial geniculate body, and the cortex. That is, frequency analysis that takes place at the cochlea continues right up to the cortex. David's battery model of Davis battery model of cochlear transduction. Scalar media has a DC potential of plus 80 millivolt. Stimulation of hair cells produce intracellular potential of minus 40 millivolt. This provides flow of current of 120 millivolt through the top of hair cells. So we have 80 millivolts and current passing and minus 40 millivolts. Structure of ampullary end of semicircular duct. Over the crista lie sensory hair cells interspersed with supporting cells. Hair from sensory cells project into the gelatinous substance of cupula. So we have the cupula, kinocilium, hair cells, crista ampullaris, ampulla of semicircular duct. Here we have the sensory hair cells of the vestibular organs, type 1 on the left and type 2 on the right. Here we have microvilli, supporting cells, nerve chalice, type 1 cell, cylindrical type 2 cells, stereocilia, kinocilium, vestibular system. Peripheral receptors, they are of two types, cristae and maculae. Cristae, they are located in the ampullated ends of the three semicircular ducts. These receptors respond to angular acceleration. Maculae, they are located in the otolith organs, that is, utricle and saccule. Macula of the utricle lies in its floor in a horizontal plane. Macula of the saccule lies in its medial wall in a vertical plane. They sense position of head in response to gravity and linear acceleration. Structure of a crista. It is a crescent-like mound of connective tissues on which lie the sensory epithelial cells. The cilia of the sensory hair cells project into the cupula, which is a gelatinous mass extending from the surface of crista to the ceiling of the ampulla and forms a watertight partition, only to be displaced to one or the other side like a swing door with movements of the endolymph. The gelatinous mass of cupula consists of polysaccharide and contains canals into which project the cilia of sensory cells. Hair cells are of two types. Type 1 cells are flask shaped with a single large cup like nerve terminal surrounding the base. Type 2 cells are cylindrical with multiple nerve terminals at the base. From the upper surface of each cell project a single hair cell, the kinocilium, and a number of other cells, cilia, the stereocilia. The kinocilium is thicker and is located on the edge of the cell. Sensory cells are surrounded by supporting cells which show microvilli on their upper ends. Structure of macula. A macula consists of mainly two parts. One, a sensory neuroepithelium made up of type 1 and type 2 cells similar to those in the crista. 2, an autolytic membrane which is made up of a gelatinous mass, and on the top of it the crystals of calcium carbonate called otoliths or autoconia. The cilia of hair cells project into gelatinous layer. The linear, gravitational, and head tilt movements cause displacement of otolithic membrane and thus stimulate the hair cells which lie in different planes. Vestibular nerve. Vestibular or Scarpa's ganglion is situated in the lateral part of the internal acoustic meatus. It contains bipolar cells. The distal processes of bipolar cells innervate the sensory epithelium of the labyrinth, while its central processes aggregate to form the vestibular nerve. Central vestibular connections. The fibers of vestibular nerve end in vestibular nuclei, while some go to the cerebellum directly. Figure 2.9. Structure of macula, the sensory end organ of the utricle and the saccule. So here we can see the basement membrane, supporting cells, type 2 hair cells, type 1 hair cells, subcupular meshwork, gelatinous substance, and otolith. This is the otolithic membrane. Vestibular nuclei are four in number: the superior, medial, lateral, and descending. Afferents to these nuclei come from peripheral vestibular receptors, semicircular canals, utricles, and saccules, cerebellum, reticular formation, spinal cord, contralateral vestibular nuclei. Thus, information received from the labyrinthine receptors is integrated with information from other somatosensory systems. Efferents from vestibular nuclei go to nuclei of cranial nerve 3, 4, and 6 via medial longitudinal bundle. It is the pathway for vestibulocochlear ocular reflexes, and this explains the genesis of nystagmus. Motor part of spinal cord, vestibulospinal fibers. This coordinates the movements of head, neck, and body in maintenance of balance. Cerebellum, vestibulocerebellar fibers. It helps in coordinate input information to maintain the body balance. Autonomic nervous system. This explains nausea, vomiting, palpitation, sweating, and pallor seen in vestibular disorders. Example, Meniere's disease. Vestibular nuclei of the opposite side, cerebral cortex, temporal lobe. This is responsible for subjective awareness of motion. Physiology of vestibular system. Vestibular system is conveniently divided into peripheral and central. Peripheral, which is made up of membranous labyrinth, semicircular canals, utricles and saccules, and vestibular nerve. Central, which is made up of nuclei and fiber tracts in the central nervous system to integrate vestibular impulses with other systems to maintain body balance. Semicircular canals. They develop, they respond to angular acceleration and deceleration. The three canals are at right angles to each other, but the one which lies at right angles to the axis of rotation is stimulated the most. Thus, horizontal canal will respond maximum to rotation of the vertical axis and so on. Due to this arrangement of the three canals in three different planes, any change in position of head can be detected. Stimulation of semicircular canals produce nystagmus, and the direction of nystagmus is determined by the plane of the canal being stimulated. Thus, nystagmus is horizontal from horizontal canal, rotatory from the superior canal, and vertical from the posterior canal. The stimulus of semicircular canal is flow of endolymph, which displaces the cupula. The flow may be towards the cupula, ampulopetal, or away from it, that is ampulofugal, better called the utriculopetal or utriculofugal. Ampulopetal flow is more effective than ampulofugal for the horizontal canal. The quick component of nystagmus is always opposite to the direction of flow of endolymph. Thus, if a person is rotated to the right for some time and then abruptly stopped, the endolymph continues to move to the right due to inertia. That is, ampulopetal for the left canal. The nystagmus will be horizontal and directed to the left. Remember that nystagmus is in the direction opposite to the direction of flow of endolymph. In other words, the slow component of nystagmus is in the direction of flow of endolymph. Utricle and saccule. Utricle is stimulated by linear acceleration and deceleration of gravitational pull during the head tilts. The sensory hair cells of the macula lie in different planes and are stimulated by displacement of otolith membrane during the head tilts. The function of saccule is similar to that of the utricle, as the structure of maculae in the two organs is similar. But experimentally, the saccule is also seen to respond to sound vibrations. The vestibular system thus registers changes in the head position, linear or angular acceleration and deceleration, and gravitational effects. This information is sent to the central nervous system, where information from other systems, visual, auditory, somatosensory, muscles, joints, tendons, skin, is also received. All this information is integrated and used in the regulation of equilibrium and body posture. Cerebellum, which is also connected to vestibular end organs, function further coordinates muscle movements in their rate, range, force, and duration, and thus helps in the maintenance of balance. Rotation test. At the end of rotation or to the right, semicircular canals stop, but the endolymph continues to move to the right, that is, towards the left ampulla but away from the right, causing nystagmus to the left. Maintenance of body equilibrium. A useful clinical approach to understand the physiology of equilibrium is to imagine that the balance system Vestibular, visual, and somatosensory is a two-sided push and pull system. In static neutral position, each side contributes equal sensory information, that is, push and pull system of one side is equal to that of the other. If one side pulls more than the other, balance of the body is disturbed. During movement, that is, turning or tilt, there is a temporary change in the push and pull system, which is corrected by appropriate reflexes and motor input outputs to the eye, that is, vestibular ocular reflexes, neck vestibular cervical reflex, and trunk and limbs vestibular spinal reflex to maintain new posture of head and body. But if any component of push and pull system of one side is disturbed for a long time due to disease, vertigo and ataxia will develop. Vertigo and dizziness. Disorientation in space causes vertigo or dizziness and can arise from disorders of any of the three systems, vestibular, visual, and somatosensory. Normally, the impulses reach the brain from the three systems are equal and opposite. If any component of one side is inhibited or stimulated, the information reaching the cortex is mismatched, resulting in disorientation and vertigo. The vestibular inhibition on one side, the example, acute vestibular failure, labyrinthectomy, Meniere's disease, eighth nerve section, cause vertigo. Similarly, stimulation of labyrinth by thermal or rotational stimulus cause vertigo. Dizziness can similarly result from ocular causes. Example, high errors of refraction or acute extraocular muscle paralysis with diplopia. Vertigo and its causes are discussed in detail in Chapter 7. Motion sickness. It is characterized by nausea, vomiting, pallor, and sweating during sea, air, bus, or car travel in certain susceptible individuals. It can be induced by both real and apparent motion and is thought to arise from the mismatch of information reaching the vestibular nuclei and cerebellum from the visual, labyrinthine, and somatosensory systems. It can be controlled by the usual labyrinthine sedatives. Thank you.